we were working on the Bellman equation last time, and I was talking about the reward vector r, which appears in the Bellman equation. So last time we had the Bellman equation for Markov chains, which I am calling the baby Bellman equation. We're going to see the real Bellman equation either today or first thing on the next class. And the equation says the value vector is the reward vector plus m times the value vector. So the value vector v satisfies this. Okay. And r are like these ongoing rewards. So they're the rewards you get at every state. And the thing we ended off with last time is that you also, this equation on its own won't have a solution. You also need to specify what happens at the end, right? And really, this equation came from how is the value vector evolving over time, right? And we really, this sum of two things was really like an honest, actual two things. It was the sum of the rewards you get now plus the rewards you get in the future, right? So you get some rewards now, you get some rewards in the future. The rewards you get in the future, their total value is like the value vector, but shifted in time by one step, which is why we had one multiplication of m, and that's where the equation came from. So there was one other thing. So this was always, but there was one other thing, which is we had these like terminal states. So we had v of x equals something for x, a terminal state. So these states where you get stuck in forever, like the last state in Snakes and Ladders, and that can be anything that's specified by the problem. I'm going to call them z for prizes. So z, this is the prizes. So z is prizes. And that matches kind of what we did in question 3. So for example, if you get a prize car, if you get to state n, then you would have the equation that v of n equals 1 because one prize car in question 3 from the lab, you get one prize car at state n, and you have v of 0 equals 0 because 0 prize cars at state 0. And in that question, there were no other prize cars. You only get a car at the end. There was no rewards at all in that problem that were ongoing. So you get v equals 0 plus mv. So this is the system of equations for the number of cars. And in fact, the bonus question was to set up this system of equations and solve it and prove that the solution is some specific thing, which was the solution turns out to be v of x equals x over n. And that was the bonus problem from the lab. Okay, so yes, I know this distinction when I'm calling something's prizes and something's rewards. They're both like things you get, right? The only distinction is the rewards you get always and the prizes you get at the end. But otherwise, they're very similar, and they had really similar equations. Yeah. Okay, maybe I'll stop saying things about them. I think I've said enough. Yeah.
Could you just go over one more time for the Gambler's Ruin? What is v representing in that the whole vector?
In this little setup over here?
Yeah.
Yes, okay. So in the Gambler's Ruin, we made v, the definition was the expected number of cars, of prize cars you get. And given that you start in state x. So you start in state x, and in the whole thing, you're going to get some number of cars. Of course, even if there are no cars, you could say this is the expected value of you, I guess, end at state n at some point. Given x0. Okay, and it's not actually, it wouldn't be the expected value, it would be the probability, right? So you have a vector which is 1 exactly at state n, and so the number of prize cars you get is exactly the probability that you end at the end. Or the expected number of cars is the probability. Yeah, and it satisfies this equation. This one has no ongoing rewards, and it has these two terminal prizes. Okay, there was another question over here. I saw a hand.
I was just going to ask if you could scroll down so we could see
The solution.
x over n. But
Yeah.
could you maybe explain a little end up with the x over n?
Yes, it's actually, I think it's, I guess what I was saying when I said solution is that the solution is x over n. To prove it is kind of annoying. And you have to involve something about the matrix M. And remember, in the gambler's ruin problem, the way I gave it to you, there were different possible betting strategies. And it's true that this will be x over n no matter the betting strategy, but this is kind of a surprising fact. So I'm telling you what the solution is. How you prove that the solution is like this is harder. For the betting strategy of the min bet strategy of either always betting 1, so you either go up by 1 or down by 1 every time, then you can kind of check that this is a solution. You can solve this, and you're going to get that the solution is ax plus b, and then you're going to be able to find this as the solution. By a is 1 over n, and b equals 0. I can post this as like a little bonus. So a few people did that case as a bonus. But yeah, maybe I should say I should say this is the answer, not the solution. Okay, let's just do that. Answer. Yeah, so in general, you won't be able to just get an answer. You'll have to put it in a computer and like solve. But in the gambler's ruin problem, it has a nice thing. Oh, and this is only when p equals a half. Okay. All right. Yeah, great questions. Any other questions or comments? Okay, so we got prizes and rewards. We've set up this Bellman equation for Markov chains. And now what we're going to do is we're going to move on from Markov chains and move on to something called Markov decision processes. And this is what really reinforcement learning is. So you can think of this line in the course is we're done with Markov chains, and now we're starting reinforcement learning. What is reinforcement learning? It's the analysis of these things called Markov decision processes. So a Markov chain or a Markov process doesn't have any decisions, and now we're going to introduce decisions. And really, it's exactly what I promised you on the first class, is we're going to take our Markov chain. We took our Markov chain, we started with snakes and ladders, we added in this idea of rewards to be able to say things about it, and now we're going to add in yet another thing, which is actions. So a Markov decision process is a sequence. It's a sequence of random variables. Random variables, RVs, not recreational vehicles, which is S0, A0, R1, S1, A1, R2, ... So you start at some state S0, you're going to do some action A0, then you're going to get some reward R1, then you're going to move to some state S1, and so on. So ST is the state at time t. AT is the action at time t. And you kind of have to make a convention on the order. The action at time t is you get to see where you are at time t and then choose your action. So you see state ST, and then you make your action. That's why I put them in this kind of order, and this matches the textbook we're sort of following. Next is RT is the reward at time t. And we think of these as sort of ongoing rewards. Of course, you can have a special rule that at the terminal state you get a prize as well. The reward at time t, and this is after action AT minus 1 and going into ST. So the example that we gave is if you want to count the number of steps it takes, you can make these rewards 1 every time you go into a state where you're, every time you move, like you roll the dice again, you get a reward of -1, we said. That was counting the states. Let me give you some examples. So it's really the sequence. We'll get a little more detailed. But let me give you some examples, just so you know what to think about as we go. And the only new thing, like you've seen the ST and the RT, the new thing is the actions. So what are the examples? The first one is any Markov chain is a Markov decision process if the actions are nothing. So for example, in the game Snakes and Ladders, on your turn, you don't get to choose anything. You roll the dice. And if you're like a little 4-year-old, you have to get reminded to roll the dice like many times, but eventually you roll the dice and then your turn is over. Like you don't have a choice. You roll the dice, that's it. So snakes and ladders is, technically speaking, it's the actions are in the action set. So sometimes people do a script A for all possible actions. So AT is some element of A, and there is no choice. You must roll the dice. So there's only one action you can take on your turn. You must roll the dice. Of course, if you're in a terminal state, like you don't move, you can imagine you let the 4-year-old roll the dice anyway, so he is happy. But you don't. Some states maybe you don't use the action at all. But in any case, you have no choice. I'll give you 2 more examples that you guys have already done. In Easy 21 in Blackjack, you have a choice at every time. You can either hit, get another card, or stick, right? Stay where you are. So this is a Markov decision process where the actions are either hit or stick at every step. And in general, you can decide based on your current situation, or you can look at the moon or your astrology and decide what you want to do. And that will be a Markov decision process. And I think you can kind of see how it evolves, right? So if you choose to hit, then the state you go to is something different, has different distribution than if you choose to stick. Okay, that's Easy 21. Another one is the gambler's ruin problem, where you can think of the bets as the actions. So the actions are bet $1, bet $2, all the way up to bet the maximum. And the maximum, I guess, depends on n. Let me write it like this. So this is the set of all possible actions. But notice that not all possible actions are available at every state, right? So you're not allowed to bet more than you have. So sometimes people will say this is the actions available at state S. You can only bet up to what you have. So even though in general you can bet n-1, at some particular state you might be restricted. You might not have all the actions available to you. Okay, and those are 3 examples. You've seen Easy 21 and Gambler's Ruin in the lab, which are real examples. Okay, I'm going to give more details in a minute, but I think if you kind of understand at a high level what's going on, it's easy to fill in the details. If I give you the details first and you have no idea what's going on, it just seems like mumbo jumbo. So please let me know. Does it kind of vaguely make sense? Okay, so very technically, you need to have a Markov property. A Markov property. And the Markov property, again, says that if you know what state you're in, then you kind of know all the stuff that happens. So it doesn't matter how you got to a certain state. It just matters what state you're in at a given time. Before, when we were doing Markov chains, that meant that there was this Markov transition matrix that takes in one state and tells you where you're going, tells you the probabilities. In a Markov decision process, it depends on the actions. So you get to choose an action, and depending on that action, it can change the outcomes. But it still has to be Markov in that it only depends on the previous state. So now it depends on actions. So I'm going to write it like this. I'm going to write it, and this is the way the textbook writes it. You have P of S prime given S. And the new thing is A. So when we were doing a Markov chain, we had the probability of S prime given S. That was what we called the transition matrix M from S to S prime. But now it depends on the action you chose, A. So you can kind of think of when you have a Markov chain, there's only one transition matrix. But in a Markov decision process, for every action A, there's a different transition matrix. And so basically, by choosing the action A, you can choose the rules of how things are going to evolve. And this is equal to the probability that ST plus 1 equals S prime, given ST equals S, and AT equals A. So the new part is the part that's in orange. You get to choose some action A, and the distribution of things that happen depends on A. And the Markov property says that knowing state S is all the information you'll ever need. The probability is unaffected if you add more things. So it's equal to that. That's the useful bit. And the if you add anything from before, and I'll write it very informally. I'll write it like this. Anything from times less than or equal to t minus 1 don't matter, right? So if you condition on like st minus 1 equals something, or you condition on some action you took like way in the past, none of that matters. If you know the current state and the current action, everything else in the past will make this an equality. So knowing the current times is enough to figure out the full probability. All of this stuff doesn't matter. All extra conditioning, you might as well erase it. And that's the Markov property. Markov property. Okay. All right. Yeah, and I think you guys understand kind of how it works, right? If you choose, you get to choose the action. Like if you know the action is I'm going to bet $2, then you can figure out the probabilities that I move to the next state. Okay. So if you have a Markov decision process, the new piece of vocabulary that we're going to learn is the word policy. Definition of policy. What is a policy? A policy is like a predefined way to choose an action at every given state. So is a choice of action for every state. And normally people write pi of s equals a, where pi is the Greek letter for p, p standing for policy. So pi of s equals a means at state s, I choose the action a. And here is the fact that is nice. Fact. A Markov decision process, also called an MDP. Let me write down MDP so you guys see it. MDP is a Markov decision process with policy pi. So if once you fix a policy pi, is just a Markov chain. So why did I spend the first few weeks of the course just talking about Markov chains? Because once you have fixed a policy, your Markov decision process, where you in principle could choose any actions, once you nail down those actions, it really is just a Markov chain. And this is what you guys did without knowing it in the lab. So in lab 1, if you do easy 21, and you use the hit below L strategy. I called it a strategy in the lab. The right word for it is policy. Policy. So it's the hit below L is a policy that you always choose to take a new card if you're below L, and you don't. You choose to stay if you're L or above, and you choose to hit if you're below L. That is a policy. And if you do the hit below L policy, easy 21 just becomes a Markov chain. That's the Markov chain you guys did in your assignment. Okay. There's the hit below L policy. That just becomes a Markov chain. For the gambler's ruin, if you choose betting sizes, if you fix the betting vector, bet size, that's a policy. That's a policy. I don't know. Arrow policy. So, as you know, gamblers are very disciplined people. So when they walk into a casino, they have a little piece of paper. They're like, I'm going to bet exactly this at this thing. They never make it up as they go. And so once they've written down their piece of paper with exactly how much they'll bet in what situations, that's just a Markov chain. There's no decisions left to make. All the decisions are like preordained by the piece of paper they brought into the casino. The thing that you guys were doing without knowing it is called policy evaluation. So here's another name for you. Definition. Policy evaluation. That means evaluate the policy, and specifically evaluate the value function. The value function. So V of S. So before we were just calling it V of S, we were thinking of, there's some amount of rewards and prizes. How many rewards or prizes do you get starting from state S? That was the value function. We're going to add one letter to it because now there's a policy pi. So we're going to say V pi of S. This is the expected value of the total return given S0 equals S. So you start at some state S. What is your total return? And it's when you follow pi. And so some people write this like here. They write E sub pi to mean I'm going to follow the policy pi. Every time I have to choose an action, I'm going to use policy pi to tell me what to do. then it's a Markov chain, and the value function is the kind of thing we've been looking at for Markov chains. That's the value function. There's one other thing that sometimes comes up, and that is the Q function. So V stands for value function. Everybody uses the letter Q for this. I have no idea what Q stands for or who chose to make a Q, but there's something called a Q function. And so it's Q pi, so the Q function for the policy pi, starting from state S, but the Q function also inputs just one action. And we could have used a different letter to describe it. I don't know what Q stands for, but it's the expected value of under policy pi, but it's the total returns. But instead of just being given S0 equals S, you're also given the action at time 0 is A. So in the V function, you always follow the policy pi. So somebody tells you, I'm at state S, you're going to follow the policy pi. In the Q function, they say, we're going to follow policy pi starting next move. So starting at time 1, we're going to follow policy pi. We're going to take the action A right now. And here's a little fact you can verify that the V sub pi of S is equal to Q pi of S pi of A, pi of S. So this is an example. So if you're following the policy pi right now, and you're starting at state S, well, then you're going to get the value function for following the policy forever. So this Q function is going to come up, and we're going to see that we want to make choices that make the Q function large. So this is all the setup for what we're doing in the rest of the course. The big question, and this is like the question of reinforcement learning, the big question, how do we find good policies? And by good, we mean ones that have a lot of value, right? Like, how do we maximize the value function? This is the big question in reinforcement learning. And the reinforcement learning is a kind of a set of methods that help you achieve good policies pi, right? And a good policy pi means like taking the best possible actions at every state. If your Markov decision process is chess, that means making good moves that lead you to win the game. So far we've seen how to evaluate policies. One way that you can find good policies, try a bunch of policies, evaluate them, and tell me the best one. So you're already like halfway there. You guys know how to do policy evaluation. Policy evaluation means finding the value function. That's what you did on your lab. But we're going to come up with more clever ways. And the reason is the space of policies can be quite large, as we're going to see. Okay, that was a bunch of definitions and like setup. Any questions or comments about that? Okay, so now we're going to do our first real example. Oh, actually, before we do the first real example, let me tell you about your final project. Because your final project is going to be exactly this question. Please find a good policy for a specific game, okay? And I'm going to have you guys all come up with a policy, and then you're all going to play and see how many dollars you get, how much value you get, and whoever has the most will win the thing, okay? So, yeah, they win the course. That's right, okay. So what is the final project? You're going to be playing Easy 21. So it's Easy 21 at a casino. Easy 21 at a casino. And what makes Easy 21 at a casino? So in the version you guys did on the lab, you were just playing a hand of Easy 21 by yourself. You were saying, I would like to end up at a high number. In Easy 21 at a casino, you play against a dealer. So versus a dealer. And the dealer will always use the hit below 17 strategy. So the way it's going to work is you're going to walk into the casino. Okay, it's not a real casino, but at the casino, you'll be dealt a card. The dealer will be dealt a card. You will choose to hit or stay until you want to stop. The dealer will play the hit below 17 strategy, and whoever has a higher hand will win, right? So if you go bust, the dealer will win. If the dealer go bust, you win. If you have a bigger number, you win, and so on. If it's a tie, and nobody wins any money. So that's what you'll be doing. And I'm going to keep track. You're going to go to the casino. You're going to have some bank roll. I'm going to keep track of your bets, and then whoever has the most money at the end will win. That's essentially what it is. There are some things that make it more exciting. One thing that makes it more exciting is that we will have a finite deck of cards. So instead of having an infinite deck of cards where it's always the same thing, that would be like your lab 1 question. You could already probably play the optimal perfect solution. If it was an infinite deck of cards, it's going to be a finite deck of cards. So you're going to have to somehow deal with that. And the other exciting thing is that I will let you choose your bet size. And so this actually makes the problem. It's a mix of Easy 21 and the Gambler's Ruin. Because at every step, you get to choose how much money you want to bet. Maybe when there's good cards in the deck, you want to bet more. And there's bad cards in the deck, you want to bet less. But you're going to choose your bet size. You're going to play the dealer. We're going to go through the deck of cards. I think I decided I'm going to do like 300 cards. So we're going to do 10 copies of that deck. You're going to play through one time. You start with some amount of money. However amount of money you have at the end is your score. And there's going to be on Gradescope, there is a function for a leaderboard. And you're going to submit your code. It's going to play against the casino, and it's going to put on the leaderboard, you played against the dealer, and you left the casino with $0 because you went broke. And then everyone will know that you went broke. But whoever has the highest will sort of have the highest on the leaderboard. How you actually do on the leaderboard is just really for fun. Like, I'm not going to grade you based on like how much money you have, but it is a fun thing to make it a little more exciting. So that's like roughly what it's going to be. I'll put out the like exact specifications soon, but that's what it's going to be. So you're going to have to find a good policy for this game. So you're going to write a function that inputs the state and tells me what to do. Do you want to hit or stick? How much do you want to bet? Those are the 2 functions you're going to have to write. You're going to choose these actions. Okay. You can use the methods in the course to try to find really good actions. All right. Any questions or comments about the high level? Yeah.
Is it just like one game, or is it like a best of like?
Yeah. So
or something?
we're gonna so it's gonna be a 300 cards. We're gonna call that one episode. This is an episode means one run until you reach a terminal state. So there's gonna be 300 cards. You're gonna have the amount in your bankroll, and it's gonna go up and down as you win and lose bets. And then at the end of 300 cards, we're gonna stop, and we're gonna count that as one episode. And of course, I will repeat it like 1,000 times and take your average like over 1,000 things, so we can it won't just be luck on who's on the leaderboard, right? So an episode equals one run through, and yeah, in practice, I will tell the computer, please run 1,000 episodes and output the average on the leaderboard. Yeah.
Are we going to be expected to have it train during runtime, or are we going to be able to pre-train it, load up all the values, and just send that in?
Yes. So this is a fantastic question. So you will do all the training beforehand on your own. So you're going to write functions that input what is the current state, like what does the dealer have, what do I have, and it's going to output either to hit or stick, and like how much to bet at every step. But the way you're gonna decide that is by doing your own sort of experiments at home and like running. So it's like you kind of like come up with a strategy before you come to the casino. You have a piece of paper with what I'm gonna do at the casino, and then you're gonna tell me, you're gonna submit that piece of paper, and then we're gonna run it as if you play. So all the training happens beforehand. That's what we're gonna learn in the course, is these methods to like learn good actions. Yeah.
Do we know the dealer's hand, or is that hidden from
Yeah,
us?
so the way it's gonna be just like in like blackjack at a casino. The dealer will start with one face-up card, just like in Easy 21, he starts with one face-up card, but the dealer goes after you. So the dealer will be showing like a 3, and you have to decide, do I want to hit or not? And then you like do your cards, and then when you're done, the dealer goes and he follows the hit below 17 strategy.
So you do everything before the dealer?
You do everything before the dealer, but you get to see the dealer's starting card.
Okay.
That's right. Yeah. Okay, so that's what it's going to be. I hope it'll be kind of fun. I am open to making it working in partners, which I think could make you guys potentially have more complicated strategies if you work with your partners. So because it's a finite deck size and you can choose your bet size, you can come up with some complicated card counting type situations, which could be fun. Yeah.
How much do we start with?
Oh, you're going to start with like $100 or something.
Okay.
Yeah. Start with 100 math dollars. Okay. Yeah, so you're going to start with some amount, and then you'll place bets, and then you want to see how much you want to maximize the amount you leave the casino with. And so, you can choose, do you want to bet all $100 on the first hand? Maybe that's a good stretch. I don't know. Okay, so that's very roughly what it is. Okay, but we're going to build up to that, so the rest of the course is going to be methods to figure out good actions in Markov decision processes, and you will show me that you know the methods in the final project by making a program that finds good actions for this specific game. Okay, so with that, I'm ready to show you guys the first example of a game where we're going to find good actions. Okay, and of course, I'm not an original thinker, so I just steal all my examples from Numberphile. Okay, here we go. So this is called The Math of Being a Greedy Pig. This is a game called Pig. Why is it called Pig? Okay, you're gonna find. I think you guys more or less get the idea of the game. And so we're gonna do two things. The first thing we're gonna do is we're gonna try to say what is the state space, right? So what is the state space for this? I told you the actions. So the actions are you can either roll again or stop. Oh, this is an important thing. In the video, they were playing a two-player version of Pig, right? There was like one player versus the other player, cumulative totals, all that. We're doing like super simplified to start. We'll build up to that. We're going to do one player and one round only. So it's just, you're not playing against anybody else. You're just trying to get as many points as you can. And I want you to answer two things. What do you think the state space is? And what kind of reward is it? Is it the ongoing reward or is it like the prize at the end? Okay. So think about how you would model this. Come up with what are like all these things, right? Like you should be able to come up with this P, this M. You should be able to answer what this question is for every action. And you got to think of what is going to be the state space. I told you the actions are either roll again or stop. What are the states? What are the rewards? That kind of thing. This is a little bit like in that rainy day, sunny day one for the 2-day one. You got to like think of like what is the thing. And then what I want you to do is play the game a few times with the dice provided. So I will give you a dice. And you will roll and play a couple times and try see if you can come up with a good strategy. Okay. So roll again. If blank, when are you going to choose to roll again? When are you going to choose to stop? Of course, the answer to this is kind of the rest of the video, but we're going to do it ourselves as well. You guys can watch the video at home. So I'll hand out these dice. Think about this. Play the game, and try and see what's going on. And we're going to figure out the best strategy, the best actions. We're going to figure out the optimal policy. That's the right way to say it. Well, let me do it. Okay, here we go. All right, there we go. It worked. Okay. So 10 people said it's 0, 1, 2, 3, and so on. 6 people said 0, 1, 2, and so on, up to times in progress or finished. Something else is a possible answer, but this one that most people chose is not a possible answer. So that one is not right. Let's take a look. So here we go. This one can't be right. I'll let you think about it for a sec. Maybe someone can tell me why can't this one be right? So if you're at state 5, okay, or at least there has to be one other state or something. Right? Why can't this on its own be correct? Yeah.
Because you don't have a state for having busted?
Yeah, there needs to be a state. So state 0 presumably means like you haven't started playing yet. So state 0 can't be the state that represents you've busted. When we were playing Easy 21, we used state 0 to represent that state. But there's no state here because we need a state where we start when we start with nothing, and we also need a state that represents where we're busted. So one way to do it, you could have done something else. You could have said all this stuff plus one more state, which is the you've busted state. Actually, even that would not be enough. So all the way up to this with even one more state saying you busted is not enough. You need one more thing. What would that be? What's the other? Yeah.
Information on whether or not the game is finished.
Yeah, that's right. So the busted would be finishing one way, but we also need maybe another state that says you won the game. So there's more than one way you can do it. You can set it up in multiple ways, but this on its own, you need to include somehow the fact, are we still playing the game or not? And I think the easiest way is to do a multiplication. So this is a set multiplication, and you have in progress and finished. And I'll draw out what this looks like for you. So let's draw a picture. And remember, you can draw Markov chains as these graphs. And so I'm going to have sort of two rows. I'm going to have the in progress row. That'll be the top row, and I'll have the done row. The done. And okay, this is state 0, state 1, state 2, state 3. So really, these states are like 0, comma, in progress, right? Like that's what that represents. And state 4, and so on. State 5, state 6. On the bottom row, I'm going to have the done states. 0, 1, 2, 3, 4, 5, 6. Okay. So this, to me, this is the most intuitive way to set it up. And when you roll the dice, if you choose to roll again, I'm going to do rolling again in blue. So if the action is roll again, I will do that in blue. And remember, when you roll again, if you've chosen to roll again, it's like a Markov chain, right? So there should be, for every state, there should be arrows going out of it that sum to 1. And if you choose to roll again, you're going to go up by dice rolls. You have a 1/6 chance of going up by 2, 3, 4, 5, or 6. So for example, this is a 1/6. This is a 1/6. All the arrows are 1/6. So why don't I just do that? So 2, 3, 4, 5, or 6. So you're at 0. If you choose to roll again, you go to all these states with probability 1/6. There's one other arrow that's missing. There's only 5 arrows here, each with probability 1/6. The whole thing needs to sum to 1. And the arrow that is missing is if you roll a 1. And when you roll a 1, you will be done. So you're going to go down to the done row. And in fact, if you roll a 1, you go down to 0. And this is probability 1/6 if you roll that. Okay. Similar from state 1, right? So state 1 has a 1, 2, 3. Oh, you can't go up by 1. You can go up by 2, 3, 4. So this is just like, sort of like in that Gambler's Ruin problem or Snakes and Ladders. You go up by these amounts, but there's this twist, which is you go to this state with probability 1/6. And that way I can keep track of, if you're still in the game, you're up here and you get to choose to roll again or not. And then when you finish, if you busted, you go down here. The other action you can take, so this is the roll again action. So you can kind of imagine these arrows everywhere. I'm going to do it in this orange color action, which is to stop. And what happens if you stop? Well, then you finish the game, so you can move down to the done row. But you don't go down to 0 points. You get to keep however many points you have. So I think about it like this. Like if you're at 2 and you choose to stop, you go down like this. And that happens with a 100% chance, right? So it's kind of a boring, non-random thing. If you choose to stop, you just choose to stop. And these arrows are 100% chance. So not all actions really have to be random. They can be random with a chance of 100%. And you can imagine setting up the Markov chain matrices for either of these things, right? There's one that moves you along if you choose to roll again, and there's one that moves you along if you choose to stop. And that way I really have it like really clearly represented if you're done or not. So this is one way to set up the game. You could set it up a different way. So you could have like, you could kind of like condense all of these things down into one state and then like keep track in some other way. There's other equivalent ways to do it, but this is one way to do it. Yeah.
Does that imply you have 2 different transition matrices that you're choosing between?
That's right. So you should, once the action is fixed, given the action, it's like a Markov chain. And so for every different action you can take, you can kind of think of there's a different transition matrix. And that's what makes a Markov decision process interesting is you're sort of given the choice between these different matrices and you get to like pick which one you want to do. And there's always some tensions about which one should you pick, right? They have pros and cons. How do you balance the pros and the cons? In a pure Markov chain, you don't get to pick. You just watch it happen, like Snakes and Ladders. But in a Markov decision process, you can always choose between roll again and stop in this case. Okay, so this was my setup. And this leads into the next question, which is, if this is the setup for the game, what is the setup for the rewards? Okay, and I told you in words, the rewards are you want to maximize the total, like you get $1 for every point you have. But how does that translate into the rewards? And let's see what people said. Okay, so slightly more than half the people did this one-time thing. If you have this set up the way I do, it's very simple, which is you get a one-time prize at these terminal states. These will all be terminal states. So these are all terminal. These are all terminal states. And you can think of a one-time prize of 1 here, a one-time prize of 2, a one-time prize of 3, a one-time prize of 4, 5, and so on. So one-time prize. So that is one way to set it up. Okay, and we're going to see next class how you can use this setup to try to find the optimal strategy. That's the kind of thing we're going to be looking at. But before we do the math of how to do it, like the math machine is going to like work and like calculate the answer and like show us the answer. but it's good to like have an intuition on what it's doing and how it's working. So before we kind of do the math answer, which we'll definitely do next class, with the real Bellman equation, that'll be next class, let's see what the strategies you guys came up with. So roll again if, and roll again if, somebody said less than 20, so roll again if you have less than 20, roll again if you're less than 12, 20 over 6. Rolling over a certain number is probably going to eventually be too greedy, right? Like if you're at 100, that's over 6. So probably maybe they had them switched. Some people did the number of turns. That's another way you can do it. I will say the number of turns is kind of contrary to the way we're setting it up as a Markov chain with the states being how much you have, right? So for example, in our setup, here is a great example. In our setup, let's pretend you are in state 4. Let's pretend you're in state 4. So you're here, you've rolled to 4, and you have to decide if you want to roll again or not. Now, in our Markov chain setup, if it really is a Markov chain, and this is the state, that means any kind of information about how you got to state 4 does not matter. That's the Markov chain like ethos. So did it take you 2 rolls to get to 4? Did it take you 3 rolls to get to 4? I guess it's impossible to take 3 rolls. Okay. Did it take you 1 roll or 2 rolls to get to 4? That information is not contained in our Markov chain. So if you wanted to include the number of turns, you would have to add that in to your Markov chain somehow. So you would say like the state is not just where you are, but the state and how many turns or something. And like there are, you can do that, but you should think carefully about, does it matter for this game? Like, does it matter how many turns you took? Okay. Let's see, what else? So yeah, some people were doing that, the number of times you've rolled. Some people have these thresholds like 15 and so on. So these people, I guess, listed out the ones where they would do it. So some people said 16, 12, 10, and so on. Some people bank every time. I like that. That's great. So good. Okay. And when do you stop? When do you stop? So some people are doing the number of turns. Some people are doing above a certain number. So try to think about what it's going to be. We're going to find the math answer next time. You can also watch the video. They will come up with some solutions in the video if you want. And we're going to, we'll pick it up next class and we'll find the optimal strategy. All right, see you guys on Tuesday. Oh yeah, and please bring the dice back.